Thank you for the introduction. My name is Tianyi. I'm from the Stable Solvers group, and I'm going to talk about using high-performance computing and numerical linear algebra to solve the quantum chemistry problem. So electron correlation, as in my title, is very important in computational chemistry because when we want to solve quantum many-body problems, typically there are two categories that we can use. One is called the density functional theory, and the other thing that, like all the other things that cannot explain by DFT will be put into electron correlation, and especially to correlate like atom things together as a group. And traditionally, there are several methods for electron correlation, and one is called the canonical method. And typically, it tries to consider the atoms and orbitals together. But we are going to use what we call the local method that tries to introduce numerical sparsity in the mathematical problem that we have. So we design parallel and stable methods to improve chemical accuracy in electron correlation, and especially for the local problems that we are going to solve. So on the right, you can see here we have what we call a Jacob's ladder of chemical accuracy, and from the bottom is that is the least accurate algorithms, and to the top is the most accurate. And we are already actually in round 5 right now. And what we have in all these methods and what we try to develop using numerical linear algebra and parallel high-performance computing is trying to improve in this round 5 that use virtual orbitals. So to explain a little bit more, for our electron correlation, we are going to start with the so-called MP2 method, and we will use it as a baseline to make more variations into what we call MP 2.5. It's actually MP2 with nonlinear variations, and then so on and so forth. If we push it to the to higher order, we can have MP3 or a couple cluster with singles and doubles, CCSD, and etc. So all we want to do is that in this round 5, we try to push it to the ceiling of this round 5 to reach chemical accuracy, like the handle of chemical accuracy. So I've mentioned several times about localized orbitals, and how it helps is that it tries to lead to grouping of molecular orbitals. So here I have an illustration of two orbital bases that we can use. So on the left, we have the canonical orbital, and on the right, we have the localized orbital, localized by a certain method called the Boy's localization. So here, the red and the blue clumps are trying to represent the localized orbital, the canonical, the localized orbitals, actually the occupied orbitals and the virtual orbital bases as basis representation functions. And so for the canonical orbitals, you can see blue and the red tend to stay away from each other, and they are everywhere. But for the localized orbitals, if we use them, we can put the red together and put the blue together, which will leads to a lot of accurate, numerical sparsity in the system that we built. So this is an illustration of how we can see numerical sparsity in the actual mathematical system that we built. So this is for the x-axis, it's the threshold, and to the left, it means that the truncation threshold is stricter. So it means numbers need to be very small for us to consider it as zeros. And for the y-axis, it's the number of ratio of non-zeros in the system that we build. So we are comparing especially the blue line, which represents the canonical basis, and all the rest of the lines that are representing various localized bases. So you can see that one type of comparison is if you fit the threshold, we can see if we use localized bases, we tend to have fewer non-zeros in the system that we have. So it's drawing a vertical line, and the cross-section will tell you that we have more zeros in the system that we built. So mathematically speaking, that if we use a localized representation, that the system or the problem that we are trying to solve is just a simple linear system, just a linear system solver with a special matrix A that has fast multiplication routines and a sparse right-hand side C, which we used all these efforts in the previous slides that we use localized orbitals to build the sparse right-hand side. But we all know from solving linear system is that even if we have a sparse right-hand side, no matter what solver that we use, especially if we just use a simple sparse linear system solver, we might not have a sparse solution. So the drawback is that we use a lot of efforts that we build the right-hand side that is sparse, and we introduce a lot of zeros to decrease computational power and to store memory usage. But after the solve, what we have for the solution is another dense, and so we lose all the sparsity that we built. And to solve this, we designed this special solver that tries to maintain the sparsity pattern of the right-hand side in the solution T. So the T building block here that we are going to use is a multiplication between the dense matrix D and the sparse matrix S. You can see in the illustration here. And for the result R, we want the result to have the same sparsity pattern as the right-hand side S. So what we do is we just take submatrix from the dense matrix D, and we figure out the sparsity pattern column by column of the sparse matrix S, and we do the dense matrix vector multiplication, and we put it in the result matrix R. That is another sparse one, and it has the same sparsity pattern as S. Okay, so once we have this sparse enforced matrix multiplication, we can put into iterative solvers such as candidate gradient in the specific example, because the A matrix that we have is positive definite. Speaking of distributed memory parallelism that we use in our solver, we use actually two types of process grid for handling our data and to build the system and to solve it. So I have I have an illustration for this simple example with CH4, which has 4 multiplied orbitals, and we are going to use only 2 computing processes to distribute the data. So on the left, we have a block-wise distributed memory or 2D process grid to build the EI matrix, and we are going to use it to build it block by block. To utilize the symmetry that in the EI, we are going to only build the lower triangular part that's represented by all these red points right here. And for the upper triangular top half, since it has symmetry, then we are going to just use the transpose to get the blocks. And the zeros and the ones represent the 2 computing processes we had that we use to build the system. So that's for the EI construction. We use a 2D process grid. And for the multiplication in the CG solver, instead we are going to use a 1D grid, because for the multiplication with that special matrix A, we require communication along the block column. So to minimize this communication, we are going to use a 1D solver. So that is a 1D block column-wise process grid. Okay, so finally, I'm going to show you some results. And first is weak scaling result, which increase the process, the number of processes with the size of the problem. And we also have a various truncation threshold plot that we show almost near optimal scaling for the sub part. And the main takeaway is that we can push the limit of the problem to very large problems that are invisible before. And if we want to use introduce the nonlinear variation, then we pay a little bit more, but we get more accurate energy approximation. And this is again weak scaling plot. And on the right, it's a comparison of this new variant with the original MP2 method. So I'm going to end the slide here, and thanks for coming, and please hit me with questions afterwards. Thanks.